All right, question 2 is pretty similar to question 1. It says find the local maxima, minima, and saddle points of each function. In part A, we're looking at f of xy is 1/2 x squared plus 3y cubed plus 9y squared minus 3xy plus 9y minus 9x. All right, so we'll go ahead and start out by finding the critical points. So we find the x derivative of f and the y derivative of f here and here. And we'll find those critical points by setting these partial derivatives equal to 0. All right, so now to solve this system of equations, I'm going to go ahead and solve for x in this top equation. So x is 3y plus 9. And then I'm going to substitute this expression, 3y plus 9, in for x in this second equation. And so that gives us 9y squared plus 18y minus 3 times the quantity 3y plus 9. Plus 9 is 0, and this leads us to a quadratic that nicely factors, and we get the solutions y is negative 2 and 1. I can then go ahead and find the corresponding values for x by just using this relationship that x is 3y plus 9. So if y is negative 2, x would be negative 6 plus 9, would be 3, and if x is 1, if y is 1, then x would be 3 plus 9 is 12. So 3, negative 2, and 12, 1 are critical points of f. And so now I want to go ahead and classify these critical points. And to do that, we use the second derivative test. So here is the xx derivative, the yy derivative, and the xy derivative. So d of xy, that's the product of the xx and the yy derivatives. And then subtract from that product the square of the xy derivative. And that's going to give us 1 times the quantity 18y plus 18 minus a negative 3 squared. That simplifies to 18y plus 9. So in particular, at the critical point 3, negative 2, d is equal to negative 27. And that tells us that f has a saddle point at 3, negative 2. Okay, at the point 12, 1, d is positive 27, and we note here that the xx derivative of f at 12, 1 is equal to 1, right? The xx derivative is just constant, and that being positive implies that the graph of f has a local min at 12, 1. Okay, so that goes and summarizes the classification. All right, now let me bring up a quick graph here of our surface. So it's a rather complicated looking surface. Kind of scan around and get a feel for it. Now I'm going to plot the corresponding points that we just found. So when x is 3, y is negative 2, if you plug those in, you find that z is negative 10 and a half. So if I plot that point, zoom in here a bit, I'm right there in that blue dot on my surface. And I know I have a saddle point, that's what I found. And I can see, yeah, that does appear to be a saddle point. If I move, say, in this direction, my z coordinate will increase. Whereas, right, if I look sort of in this angle, right, from this perspective, I can see if I move along, say, one of these contours, my z will decrease, right? So this is neither a max or a min, right? It's a saddle point. Okay, the other point of interest is when x is 12 and y is 1. If you plug those in, you find that z is negative 51. So I plot that point, zoom out. I'm right over here. Zoom in here a bit. I can see that the surface appears to bottom out at this point, and that's where I have a local minimum. Okay, very good. Let's move on then to part B. So for part B, we're looking at the function g of xy is 1 minus cosine x plus y squared over 2. So again, we'll find the critical points. The x derivative is sine x, the y derivative is y. And so if I set these equal to 0, well, if sine x is 0, then x must be an integer multiple of pi, right? So 0, pi, 2 pi, 3 pi, 4 pi, negative pi, negative 2 pi, negative 3 pi, and so on. Okay, and here y has to be 0. These are the critical points of the function g. Notice here there's actually an infinite number of critical points, right? Because k can be any integer. All right, so now let's go ahead and classify these critical points. We use the second derivative test. So the xx derivative of g is cosine of x, the yy derivative of g is 1, and the mixed partial is 0. So our quantity d of xy, that will be cosine x after simplifying. So I'm going to break this up into two cases. Okay, so if k is an even integer, okay, so in other words, if we're looking at the points 0, 0, 2 pi 0, negative 2 pi 0, 4 pi 0, negative 4 pi 0, and so on. Okay, if I plug k pi in for x, right, I get the cosine of k pi. K is an even integer, that's going to equal 1. So here, the quantity d is positive, and the xx derivative of g is cosine of x. That's also 1, so that's positive. G then has what? Well, d is positive, the xx derivative is positive, so we have local mins at these points where k is an even integer. All right, so now what if k is an odd integer? Well, now the cosine of k pi will be negative 1. And since d there is a negative number, that implies g has saddle points at these locations when k is odd. All right, so let's jump over to a graph there. So here is our surface. Okay, now notice from that quadratic term in y, you kind of see a parabolic looking shape, and then this cosine of x term you can see kind of gives rise to some oscillation there, right? So kind of an interesting looking surface. Now I plotted a whole bunch of these critical points that we just found, and you can see they are at these blue dots, kind of scanning through. And so just to zoom in on a couple of these, so for example, at 0, 0, well, that's where k is even, right, when k is just 0, and we found that we have a local minimum there. And yep, just kind of scanning through this surface, yeah, that is, as we can see, a local minimum. Now if we jump over to say when k is 1, so if k is odd, that's going to be at this dot, zoom out here a bit, that's going to be at this dot right here. And from this view, I can see, yeah, if I move like this, my z-coordinate would increase. But then from this perspective, right, if I move like that, my z is going to decrease. So that would be a saddle point at that dot. And you can, if I zoom back out, you can see there's sort of this alternation between saddles and minimums, right? So at these bottom points, we have these minimum points. And then when you reach one of these little peaks, these little ridges, those are all saddles. So yeah, kind of interesting there. Well, that's going to do it. And I will see you in the next video. Thanks so much.